We are familiar with the derivative formula, and the first order derivative of a function f can be expressed as the limit of this slope, the difference, horizontal difference of a function from x to x plus h, and the vertical change in the function is f of x plus h and f of x. So the ratio of y change over x change when the h is taken to 0 is called the derivative at some point. Suppose that we are able to take the derivative by k times, and what happens if I do the job once again? This is k plus 1th order derivative of this function. We'd like to make use of mathematical induction to find the value, the expression for the kth order derivative. Before that, we'd like to extend the idea to compute the second order derivative. The second order derivative is the derivative of the first order derivative. So I substitute the complete expression in here to here. And the difference between this is I have shifted x0 by h. You know, 1x0 is given in here, plus h is replaced. x0 plus h minus fx0 plus h. Okay, so I substitute this one in here and substitute this one in here. The result is that h2h minus h. Okay, the previous one is this. I find this negative sign, this negative, they adds up in the middle. Therefore, it is 2h, h, nothing, just something like that. And then 1, 2, 1. You are familiar with this. This is a binomial coefficient, except that your sign is oscillating. Okay, if it is, let's see if it is true. If I'm right, it should be 1, 3, 3, 1, and plus minus plus minus. Let's see if it is true. I make use of this. 2, 1, 0. That's fine. And I need to shift by 1. The 2 becomes a 3, 1 becomes 2, 0 becomes 1. Okay, and subtract. The first one, 3h, minus 2 minus 1 minus a 3, and then plus 1 plus 2 plus a 3 minus. All right, my guess was correct. Then it should be 1, 4, 6, 4, 1. As Pascal told us, Pascal's a triangle. Sum. Okay? So, let me take a guess. This has a binomial coefficient. And the sign is flipping. In the argument, it is increasing by 1 from here. 1 to 0 to n. Okay, and from 0, it oscillates from, this sign oscillates. Okay, if it is true. This was our guess. And substitute this one in here and shift this coefficient of h by 1 that is here. Comes from this, and this is this. So this is carbon copy. I subtracted, and this is the same except that I have shifted this h. Everything is the same. Now we'd like to add these two, keeping this part the same. At the moment, they are different. So I have separated, I have shifted this one. This one, if I substitute k equals 0, it begins with 1. So what I have done is replace this 1, k plus 1 with k, and then let it begin not from 0, but from 1. Because of this, I have replaced effectively k to k minus 1. Because of that, k has been shifted by k minus 1, and n minus k minus 1 is n minus k plus 1. Okay, everything is fine. So I can combine these two terms, except that you need to be careful. The starting point and points, they are different. So you need to consider the beginning and end points. So k equals 0 is missing in the first sum. So I need to single out the k equals 0 term outside. That is here. And at the end, we need to consider the n plus 1, the number n plus 1. We should be careful. So at the end, we have this term and this term outside. And from 1 to n, we have two terms that can be summed. And this one is simply shifted 1 by 1, coming from Pascal's triangle. And proof is given in explicit form. As a result, I can combine the two terms, and finally the expression is proved to be the same as our original guess. Therefore, we can conclude that this formula can be used repeatedly to extend the region of extrapolation by h, 2h, and nh, and so on. In addition, the coefficients of power series are all derivatives. First order, zeroth order, first order, second order, nth order. And using these common factor, I can solve this linear equation to find the expression for the shifted function's value by shifted amount, value of a function at some point, that is f of x, 0, and value of a function at x0 plus n times h. I can make an extrapolation in terms of the power series in h. the result is remarkably simple, this one. And you can follow the calculation with ease. And what's that? This is according to binomial expansion. It is nothing but this. And what's that? If I take the limit as n goes to infinity, this nh can be expressed as nh divided by n. And if I want to keep this nh by a finite value that is now expressed as a, in that case, it is nothing but the expression for the exponential. Instead of a number, what we have is the derivative of exponential. Exponential, some parameter multiplied by a derivative operator. So what we have done is the proof of Taylor series expansion using a very simple algebraic way.